Okay, so this is part B. So we're gonna be introduced to new equations, formulas. I know you guys are getting tired of more additional formulas, but here we are. So this is just to find the distance, almost like finding a norm, if you will. But this is more complicated because we're trying to calculate things that are outside of the plane, right? So we don't want to use norm because norm. Remember? And you should know that Cauchy-Schwarz inequality concept says that those equations perpendicular and parallel only applies if they're on the same plane. We are now dealing with a completely new scenario where we have to think outside of the plane. So that's why we have to resort to other formulas, right? So, anywho, so you have two equations. They're really similar because the concept is exactly the same. So this one is in the plane with IR2. Or two-dimensional, so I think it's still a plane, but they call it a line. Not wrong, but whatever, right? So this is two-dimensional, right? Which makes sense. So you have this linear equation, right? Ax plus by plus c equals 0, and you have a plane of x and y direction, right? Because it's two-dimensional, right? There's no z, right? So because of that, yeah. So that's all there is, and you just need to know how to scrap the values of your interest. So A, B, C comes from the coefficient of each entries, and then the X and Y is going to be your plane, numbers within the plane. Now you have to be the thing that really confuses me from time to time, not because I don't know, it just makes some stupid mistakes. I keep putting X and Y in here because it fits perfectly, right? But position-wise, but no, you gotta be careful here. So I made some mistakes like that on my homework assignments, and fortunately I didn't make that mistake on the quiz, but I can see how some people might get confused, might make that kind of silly mistake. So try to avoid that, bear that in mind, okay? So this one is the same thing, but it's three-dimensional, which is reflected because the plane now has x, y, z, right? So virtually the same thing, right? So yeah, so let's try on what am I saying? Let's go to question 21. So here, question says, find the distance between point and a line. So whenever they say the line, the first hint should be, oh, I'm using this equation because the plane is a line, right? And there's other hints too if you look at the equation. So this is what we're given with, okay, right? So you see that the equation is x and y, right? So I only see x and y, therefore it must be two-dimensional, right? So therefore we must be using this equation. So set that equation up and plug it in the appropriate numbers. 4, 3, and 4, A, B, C comes from the equation, coefficients of each variable. So 4, 3, and 4, 4, 3, and 4. And x and y will be the point given from the plane. So negative 3 and 1, negative 3 and 1. And then the bottom is going to be A, B, so it's going to be 4 and 3. Yeah. So that's all there is. Now, technically speaking, because we've run into some situations like this, right? Square root of 25 could be 5 or negative 5. So shouldn't this be 1 or negative 1? We can't, because distance always must be scalar, must be positive. You can't have a negative distance that we know of, right? So once you get into quantum mechanics, you might run into some bizarre concepts. But we don't have to take those chemistry courses, so we don't have to worry about that. Or, I don't know, some people might be taking this and they're still in science major, so those will have exception. But that's all there is. So nothing too difficult. We'll try another question just to be comfortable, but again, I think you guys got the message. Okay, so question 24 is what I did. So similar idea, so just follow, if you listen to the earlier question thoroughly, then this is a pretty simple cake. It's a simple piece of cake. The only minor difference is that the 5 is up here, but just simply move the 5 to the other side so that you have the right ratio, right? So I didn't bother, if for some of you it comes naturally, but this is same thing as 3x plus y minus 5 equals to 0. I'm just moving 5 to the left side, right? In that case, the c will be negative 5. So that's all there is. Nothing too difficult, right? So, anyways, so you have that. And then 25, again, so on the question, so two hints, right? 25 says, find the distance between point and the plane. So when they say that, you know that's going to be three-dimensional, right? Prepare to use this equation. Also reflected by the fact that the equation has x, y, and z, right? So we're just going to go through. So it's going to be first one, second one, third one, and the very last one. I know it says 4, but if we move to the other side so that it equals to 0, it's going to be negative 4, right? So divided by 1, 2, negative 2, square root of all this stuff. and then you have 5 over the square root of 9, so that gives you 5 over 3. Not negative 5 over 3 because that's not distance, right? So distance has to be scalar and positive. Or scalar means positive, but nonetheless. So that's that. I'll do 26 too, just so that we're comfortable. But this should be now firmly embedded in our brain. So okay, so this is question 26 and 27. So 26 is the same idea, right? So I just did it again just to be sure, right? So just go through. Just bear in mind that on the top they're going to be negative, right? So it should be negative 23, but it's under absolute value, right? So it will be 23, right? So that's that. 27 is where things get a little interesting. So basically the question saying gives you two equations and then they want to find the distance between these parallel plane. Okay, so I guess technically we should be checking if they're parallel or not, but since they said they are, so let's just go with it, right? So we have these. So we're starting here, but here's the problem. We don't have an equation that lets you do plane to plane. That may come up later, I don't know. But all we know is from point to a plane, and that's where the D equation, all this came from, right? So we gotta use it somehow. So how do we do that? There's one way to do it is let's just find a point in the plane. And then, there's two planes, right? Just choose one and find a point. Let's say I chose this one, right? Which I did. Find a point that exists on this plane, and that this point, distance from this point to this plane, that should be the same as the distance between this plane and this plane, right? So what I mean by that is, I'm assuming you checked the 26 by now, so I'm gonna erase it to make some room. I think you guys know what I'm saying, but basically the issue is what we're trying to do is there's two planes that are supposedly parallel, and so they should be, I want to know the distance in between, right? But let's say there was a point I chose that exists on this plane, right? And these two are the same thing, but I'm just not drawing the point. So isn't distance between this same as distance between that? We learned how to do this, right? A while ago. We did plenty of that, right? So if I can find this distance, wouldn't this distance be equal? And therefore this distance will all be equal? So that's the point we're trying to get here, right? So, and this was, I don't know if it was on a quiz, but why not, right? This is a good quiz material because it makes you think. Anyways, so because of that, so you can't do plane to plane, only point to plane. So I chose this equation. I like this one because it looks simple, right? So I want to save this for questions here. But again, ultimately, it doesn't matter, right? You should get the same answer either way. Okay, so anyway, so you have that. So I chose this plane to find where the point is, right? So I'm arbitrarily going to select the point. So make one point. So example, I just do x 0, 0. Because I just like a lot of zeros, right? Just like when we do elimination for linear algebra matrices, right? So the reason why I didn't put 1 is I don't know if 1, 0, 0 will exist in that plane, right? So that's why I left this one as a variable, right? So I'm going to actually manually plug this into this equation. So 4x 0, 0 and must equal to 12, right? So if that's the case, let's see. What x value has to be? X has to be negative 3, right? For this to be true. So negative 3, 0, 0 exists on the plane, on this plane, right? So now that I found the point in this plane, I found this point in the plane, I'm just going to find the distance in between. So I'm going to use this point, and I'm going to use this equation, right? You cannot use the same plane though, right? If you use this plane to get an equation, you cannot use this plane, because that's like saying distance between this point and the plane. It should be 0. Actually, yeah, that's a fun thing. That could be a nice question. Potentially good material to make a good question. But nonetheless, so because of that, nonetheless, we got the idea. So we're using this point and we're using this plane. Not this plane, because we use this plane to get the point. If you use this equation plane to get the point, then you must be using this plane, right? So make sure you don't use the same point from the same plane. So anyways, so I'm using this point and this plane, so then the rest is pretty simple, right? What we've been doing. So 2, negative 1, negative 1, 2, negative 1, negative 1, 3, negative 3, 0, 0, negative 3, 0, 0. So that will give you negative 11. The whole thing is negative 11, but it's absolute value, so it's going to be 11. The bottom will give you square root of 6. That's your answer. Done. I'll do 28 too, just so that we play safe, but not too difficult, right? Not once you get the concept. So 28. Okay, so on to question 28. So it's similar as 27. I just did the same thing. I just chose one plane, and it doesn't have to be x. I just use x just because that's but you could use 0y0 or 00z. Doesn't really matter. On the solution, I think they use 00z, but really shouldn't matter, right? So I just did that to find a point. So x is 1 over half, so it's going to be 1/2, 0, 0. This exists in this plane, right? So therefore, I just use this equation and this point, done, right? So, same idea. 29 is where it gets a little bit interesting. And I'll be honest, this was the only question. This was the only question that I wasn't 100% sure how to do. So, yeah. So thank you, Carl. No, I didn't ask Carl this time. I asked Digby this time. It's a joke, but when Digby retires, our math grade is going to plummet. Oops. Yeah. So we'll see. I know the math department is preparing for his replacement soon because he should be retiring. But we'll see how that plays out. Yeah. But anyway, so on to 29. So 29 is a little weird. We haven't seen that kind of questions before. So it's asking, find the unit vector that is orthogonal to both vector u and vector v, where vector has these vector components, right? So how do we go about doing this? That is the weird part, right? So this is where I got struggle. So basically what we try to do, we try to make sure that 29 find a unit vector. So find another vector that is orthogonal to both this and this, right? So we just said let W be some another vector, right? So we're trying to find out. So we want to make sure, first of all, first condition is it has to be orthogonal, right? So that W has to be orthogonal to U vector and the V vector. Well, that's easy. That part is easy because how do we check if the vectors are orthogonal or not? Dot product, right? So because of that, so I did the dot product right here. So so this should be orthogonal to this, and this should be also orthogonal to this. So dot product this, dot product that, they both must be 0. So let W be just x, y, and z, just something generic, right? Because we don't know what the answer is, right? So let's just check. So if these are orthogonal, so I'm gonna do dot product, right? So that's gonna be x plus 0 plus z, right? So that should be 0. So in this case, we can say x equals to negative z, right? And we're going to do the same thing for the v, right? So it's going to be this times this, this, okay, fine, it won't be times, it will be dot product, right? So if we do that, that's going to be, x is going to disappear because it's 0. 1 times y, y is there. 1 times z, z is there, right? So again, we did this, right? Now, interesting enough, negative z equals, so x and y both equal to negative z. So what does that mean though? Because I don't know what that exactly means. The important thing is we're looking for unit vector now, right? So that's going to really help. So unit vector equation, if you remember, it was a while ago. Remember it was, unit vector was 1 over w, and then you just times it by the vector of w, right? So that was a unit vector, right? We're trying to find this guy. We already know what this is. That's going to be x, y, and z, right? Which we will have to change eventually, but we'll get to that. We'll get to this part first, right? So that is going to be right here, right? You guys can see sort of barely. I'm gonna. Okay, so hopefully that gives you a little more room. But anyways, so that's going to be x squared plus y squared plus z squared, right? We found a norm before, right? Here's the thing though, these don't mean anything. So this is where this comes into handy. Oh, x also equals to negative z. Y also equals to negative z. So I'm going to replace x and y with negative z's. And if I do that, I get, because again, we don't care if it's negative or positive because we're going to square them, right? So you're going to have z squared, z squared, z squared, add them up, you're going to have 3z squared, right? Now we say this has to equal to 1. Why is that? Because this is going to be your unit vector. This is going to be our unit vector, right? Unit vector literally means, scale 1, right? So that's what we meant equal to 1. So therefore, isolate for z, and you're going to have z equals to positive or negative 1 over square root of 3, right? Now, we had that before. So this thing. So let me rewrite here. So this thing is gonna. Oh no, not that. So z is going to be positive negative 1 over square root of 3. Okay, so where do we go from here? So basically we know it's this one. So let's see. Then now that we have this, we're gonna try to now get the unit vector, right? W, remember, was vector was x, y, and z, right? But reality, we can change that so that it becomes negative z, and z, right? So basically, all we're going to do is to so that's gonna be this, right? And this whole thing is gonna be this, right? So, oh yeah, by the way, there's a better answer. If you weren't sure when I said the y it has to equal to 1, it's because how do I say this properly? Okay, so that by definition unit vector means it has to equal to 1, but I'll try to explain better as to what it means. Let's see. I think that explanation is pretty clear though, right? I mean, if we want this new unit vector, you're gonna have 1-to-1 ratio, right? You've got to, right? Like you can't have 1, 2, 3. You have to have 1, 2, 3, 4, 5. Those scales of 1, right? You can't have 2, 4. So okay, maybe I will overcomplicate things. It might be because I'm sleep deprived for a while, but nonetheless. So if that's so we do that. So that's again, equals to 1. So okay, maybe there's a better way to show this. Okay, so let's try this again. So basically, so if I have W equals to 1, right? So if that's the case, so we know this is gonna be, yeah, okay. So, okay, maybe this is a better way. So instead of doing that, we have this, right? So if that's the case, so, oh yeah, this is a better way to do it. What was I thinking? Okay. Instead of trying to find the z, right? We don't have to do that. Okay, never mind. Okay, there's a simpler way to do this. So we already said, okay, forget equals to 1, okay? We're just saying, let's just find this guy, right? So this w, right? So if that's the case, then we just do that and we find, so here we say this equals to 3z squared, right? That's all we have to say. Where the z yeah, so if, okay, let me try this again. Yes, okay, so yeah, let's do it this way because it makes more sense. So let's just plug it in. That way mathematically it makes sense. So we have that and we have this, right? So let's literally just plug in what they have here. 1 over this is going to be 3z squared, right? Or this, or it could be just z. It really doesn't matter. We're just rewriting it, right? So this is the same thing as this, right? So that times vector, which is going to be z, z, and z, right? So remember, this is plus or minus, right? So we forgot to mention that, plus or minus. So because of that, so that's going to be, so times it together, z is going to cancel each other out, right? So it's going to be just 1 over root 3, 1 over root 3, and because this is negative, so these are negatives. If this is positive, right? If it's positive, but this positive times positive will give you 1 over 3. So you can either have that, but remember, so vector could be both direction, right? So because of that, so if this was now negative, right? So if that's the case, then we're just gonna have the same thing, but it will be opposite direction, right? Negative. So give me these two, right? So those are the unit vectors, right? So yeah, so that was the really complicated one. Yeah, so hopefully what I explained earlier didn't really confuse you. If it did, then just follow by these rules, right? So you literally just find the norm of W, which will give you that, which will equal to this, right? So so it's going to be plus or minus, right? So if you do that, so this is the same thing as plus or minus Z, right? Or so we'll just put the signs in front, right? So this could be plus or minus. So if it's plus, it's gonna give you this. If it's minus, it will give you this, right? So, okay, so that's wraps up 29. Yeah, let's go to 30. It's the interesting ones. Okay, so we're on to question 30. This is a nice break from the hard ones that we're gonna do in the future. So. Let's look at it here. So question 30, so we have two vectors, right? Vector v and vector w, excuse me. And then, so they have a, b, and negative b, a. So basically it's asking, give me, tell me, for question 30a, tell me why these two are orthogonal to each other. So every time when we check the orthogonal test, as we should all know by now, is going to be dot product, right? So I'm going to do a dot product of these two vectors. That must be 0 for it to be orthogonal. So I'm going to just do it. First entry, a and negative b plus b and a. So that's going to be negative ab plus ba. These two are the same thing, so add them up, and then it's going to be 0, right? Oh, by the way, if this was a matrix, then that's not necessarily the case, right? We can only say that because these are just numerical entries, right? So anyways, so because of that, that's pretty simple. B, they're basically saying, use this idea. So you see what they did here, right? So if whatever this is, they switched it and made one of them opposite signs, right? So if that was the case, using this concept, give me two vectors that will be orthogonal to v, which happens to be 2, negative 3. So again, dot product, right? So I chose two vectors that will be orthogonal. One is I just use the same concept, right? So whatever this is, 2 and negative 3, I'm going to flip it so that becomes negative 3 and 2, and then make this one opposite sign, so it's going to be 3, 2. And when I try that, it works. Another one is the negative 3 and negative 2. How do I do that? Remember, 3 and 2 is orthogonal, or not orthogonal, so this is just a vector, right? What's a vector? Same vector but going opposite direction, right? Remember that one? I think that one was basically v equals to k, like that, right? So like that. So, and I just said k is going to be negative 1. So that's virtually identical. So all I did was I put negative in front of for both of these, right? And I tested it just in case. And it works. This is going to be negative 6, this is going to be 6, will equal to 0. So those two will suffice. And see, you're virtually doing the same thing, but with a different vector. So now you have negative 3 and 4. But again, we know the drill, right? The concept is clear. So I'm going to flip it and make one of them opposite signs. So that's going to be 4, negative 3. And then I put a negative in front. So it's going to be negative 4 and negative 3. So that's one. And the other one, I could just make same vector going the opposite direction. So opposite of that is going to be 4 and 3. And I haven't bothered checking this, but I'll check one, I guess I could. So this one is negative 3. And then 4 plus 4 and 3. Yeah, so that's going to be 0, right? So they're orthogonal, right? So nothing too difficult. But if you appreciate this effect now, right? This concept now, on a test, maybe you'll be able to pick up a pattern like quicker, right? So interesting concept that they showed us, but something to maybe remember for the test. On to 31. Okay, so for question 31, basically they give you the points A, B, and C as shown here. And these are points because they're not equal signs there, right? Those are just coordinates like your GPS. they are not vector, and these are not vector entries. But nonetheless, the question is asking, do the points A, B, and C form the vertices of a right triangle? So it's a triangle, but does it create the vertices of a right triangle? So we're gonna see. So the points themselves will not be helping us with this particular problem. In order to check whether the triangle is right triangle, right? We need to know the lines, right? Because and the keyword is right triangle is orthogonal, right? Perpendicular. So out of two triangles, right? Out of two horrible, yeah. So if it's a triangle, I need to have one of these three that needs. So let's say this was A, B, and C, for example, right? Either A, B, and B, C, or has to be orthogonal, right? Now in this case, I put A, B, C here, but it really doesn't matter, right? So A, B, and B, C, or A, C, and C, B, or basically, if any one of the two vectors that are possible have orthogonal relationship, right? Then we know it's a right triangle. And how do we figure out whether it's two lines make an orthogonal relationship or not? Dot product, right? So first we need the lines, right? We need these lines. So A and B. And basically that's just subtracting, right? Just like finding a vector, right? So basically I just did negative. So it's A to B, right? So again, final minus initial, right? So because of that, negative 2 minus 1, it's going to be negative 2 minus 1, 0 minus negative 1, 3 minus negative 1. So that's going to give me these vector components, right? Negative 3, negative 1, negative 2. Here, this is a vector now because these 2 points now make a line, right? So they go with a direction, right? So that's that. And so I'm going to calculate for BC, which is going to be B to C, so final minus initial, negative 3 minus negative 2, negative 1 minus 0, 1 minus 3, so it gives me this vector for for line BC. And the last one we need to check is AC. Yeah, so that's going to be from C, final is C to A, so it's going to be negative 3 minus 1, negative 1 minus 1, 1 minus 1, so you get these, right? So if one of them ends up becoming a 0 when you use them as a when you go through a dot product process, then you should be right triangle. So I don't know. Oh yeah. So A, B, B, C, and AC. Those are the only possibilities. There's no other lines that we can possibly draw from these three coordinates. So yeah. So where do we go from here? So we just do so I start with A, B, and B, C. But if you do that, and luckily. You guys know I have to do the dot product by now, so just follow through and equals to 0. So yay, okay, we got really lucky. So it's 0. So if A and B, C are orthogonal in triangle ABC, then ABC must be the triangle, right? So you don't have to be this wordy, but you get the idea, right? Now let's say AB and the BC didn't work. That doesn't mean it's not a right triangle anymore, because the condition is we just have to make any two lines orthogonal, right? So if AB and BC don't work, try BC and AC. Or you could try AB and AC, right? So, so in this particular case, we got lucky, but in 32, hopefully it will give us a bit of a more difficult challenge. So this is 32. I was hoping that AB and BC doesn't work, but maybe it has a magical combination or something. So I tried number 32, same situation, right? They give you 3 points, so I drew up 3 lines, and I tried dot product of A, B, and B, C, and again it becomes 0. So, okay, we're getting lucky, but I'm trying to find a good example, but it's not giving me. But yeah, just an FYI, A, B, and B, C don't work, that's okay. Try A, B, and AC, or B, C, and AC, right? All we care about is using any one of these 3 vector components, vector lines, right? If one of them ends up being orthogonal, that must be a triangle. So that's what I'm trying to say. But the problems are not, very useful, in terms of what I want to do. But let's try number 33, and we are done. Oh, I'll also have to upload the quiz 3, so hopefully we can make that happen soon. Okay, so this is question 33. So again, basically they say the vector v is orthogonal to vector w1 and vector w2. So basically prove that k1 and k2 be any real scalar if this is true, because vector v is and this whole expression is orthogonal. That's why it equals to 0. So we need to prove why, right? So how do we do it? Well, they already said vector v is orthogonal to vector w1 and w2, right? So we know these two must be true, right? Because they're orthogonal. So let's go back to the original formation. So if I do this, that same thing as just like timesing the if you remember, like when you times like something like this, I forgot what's called. Opposite is expanding, but yeah, when you simplify a factorial, like expressions, you just times by this and times by that, right? So that still applies. So it's going to be this times k1 w1 plus v vector dot product k2 w2. Well, k is a constant, right? So we can take it out. This one in one of those theorems. So if we take out the constants, right? Because this is just a product, not a dot product, right? So if we take the k1 and we take the k2 on, you have a dot product of v, w1, and v and w2. And remember, these two are 0 because we said this, right? So because they are orthogonal. So that's going to be k1 times 0 plus k2 times 0 is equal to 0. That's why k1 and k2 can be any real number, because 0 times anything is 0. We don't care, right? So 0 times whatever is 0, 0 times whatever is 0. So 0 plus 0 will always be 0. So that's why there's a very little restriction. The only restriction I can think of is like if k is undefined number, unreal number, like something over 0 or something like that. But apart from that, everything should work, because 0 times anything is 0. So that is that. So that wraps up the 3.3. I will upload this as soon as I can, and I will start working on reviews for quiz 3.